So we're going to look at this curve, this x cubed minus 9x squared plus 18x curve. And what we're going to do is we're going to look at what it looks like when we look really close to it. When we're going to try to use this red line to approximate points on this curve. Okay, so why are we going to use a straight line to approximate points on the curve? Well, first of all, straight line is very easy to use. Okay, it's a linear equation, and sometimes these powers are hard to work out. And the other point is that as we zoom in to this point, as we zoom into 0, this curve looks straighter and straighter and straighter. So as long as we do this straight line approximation relatively close to the point where we have this tangent line, okay, this approximation is actually going to be fairly good. Okay, so this is a big idea in that as we zoom in, any curve starts to look more straight. So this straight line, the red line here, is an approximation of our curve as long as we're close enough to the point of tangency. Okay, so that's the main idea here that we want to make sure we understand. Okay, so how are we going to actually do this? We're going to actually calculate some values. So we're going to try to estimate this green point here on the actual curve using this red linear equation. Okay, so to do this, we need to come up with our tangent line equation. To get the tangent line equation, we need two things. We need the coordinate. We need one point on the line. Okay, so we're going to use the point of tangency, and we need to know the slope of this line. So we're going to need a derivative. Okay, so as we look at this point here, the known coordinate is going to be 0, 0. Okay, at x equals 0, y equals 0. So there's that purple point there. That purple point represents my point of tangency. To get the derivative at that point, what we need, or so the slope of that point, we need to work out the derivative. Okay, so we work out the derivative of that function, and we actually calculate the slope at that point. So the derivative is 3x squared minus 18x plus 18. And as we plug in the point x equals 0, we can work out the slope of 18. So the equation of the tangent line in general looks like this. Okay, it's going to be the slope times x minus x naught plus y naught, or f of x naught. Okay, so this is our linearization of a point, sorry, of a tangent line. Okay, this is our tangent line linearization. And we're going to use this line to approximate points. So when I plug this in, okay, I know that my slope is going to be 18. Okay, so I plug in my coordinate of 0.2. Okay, my original x naught is 0. And my y naught is 0. When I actually plug it in, I estimate the value of y at x equals 0.2. So this value of y we don't know, but the red line is going to be approximated by this equation, okay, this linear equation, and we get a value of 3.6. Okay, we can see it over here as well. We can see that the change in y here is going to be calculated by that change in x times the slope. Okay, the change in y is 3.6, and that actually represents, since we're starting at 0, that actually represents the y coordinate. And you can see that it's above that line. Okay, so it's above that green point. So it is an overestimate. And if we actually calculate the real value of f of 0.2, it's about 3.25. Okay, so we plug it into this black curve, okay, which is this original cubic equation. We get a value of 3.25, and that estimate that we use with the linear equation of 3.6 then represents an overestimate, which is what our graph indicates. Okay, so we can actually do this to help us deal with functions that are much more difficult to deal with. So how do I calculate sine of 1? Well, I could plug it into a calculator, but unless I know what the value of sine 1 is, how do I actually calculate it? Okay, how do I actually do it, add, subtract, times, divide to calculate this value? It's actually kind of hard. So what we can do is we can just say, well, here's my curve of sine x, and I know the exact value of this purple point here at pi over 4. I know the exact value of sine at that point. Okay, that sine of pi over 4 is 1 over root 2. So I know the x and y coordinate at that point. Furthermore, I can calculate the exact slope at that point as well, okay, because I know the derivative of sine, and I can evaluate that derivative exactly at that point. Okay, so that's what I'm going to do. I'm going to find the tangent line, the red tangent line equation by, well, first of all, I have my coordinate, okay, pi over 4, 1 over root 2. I can get the slope of this tangent line using the derivative of cosine. So the slope works out to be 1 over root 2. It just happens to be the exact same as the y coordinate. So I have my slope, I have my coordinate, my tangent point. I can come up with the equation of a tangent line for this. Okay, so in this tangent line will approximate values of y on this black curve as long as I'm close to that point of tangency. Now it's not going to be any good way down here, but anywhere close to that point of tangency, it's actually a pretty good approximation. Okay, so y equals, well, my slope here. Okay, so this is my tangent line equation, which I'll write down. Okay, so y equals, my slope was 1 over root 2 that I calculated from my derivative. Okay, my known coordinate is this pi over 4. Okay, so where's that pi over 4 coming from? Where's my purple? It's going to be minus pi over 4. Okay, and then plus the known y coordinate, 1 over root 2. So this equation will approximate points on the black curve of sine x near the pi over 4 angle. So since 1 is somewhere, it's not super close, but it's close enough to the pi over 4 that we're going to use that as our linear approximation point. Okay, so we're going to then find out the y value when x is 1. And this is going to be approximately equal to sine x. So I'm just going to maybe write it like this. Oops. Okay, so get rid of that. Okay, get rid of that. So I'm just going to write it like this. So I'm going to write this as sine x. Sine x is approximately equal to y at 1. This y value at 1, if I plug it in, it's going to be 1 over root 2, 1 minus pi over 4, plus 1 over root 2. Okay, now plugging that into a calculator, I can use an add, subtract, times, divide equation then to calculate this sine value. Okay, and it's not actually the actual sine value, but it's pretty close. So I go 1 divided by square root 2 times 1 minus pi over 4 plus 1 divided by square root 2. Okay, and it gives me a value of about 0.86. So this is equal to about 0.86. Okay, so what we're estimating then is we're saying that sine of 1 is approximately equal to the y value at 1. So we're saying that this coordinate on sine is going to be approximated by that linear equation as long as it's close enough to the tangent point. And this is our approximation of sine 1 is 0.86. Now, if I actually use a little bit more accurate value, sine of 1 really is 0.841. Okay, so the actual value is equal to 0.841. So we're a little bit off, and we can see that the actual value is actually a little bit below, right? Okay, which our diagram actually confirms that it's a little bit below, but it's not too far off. And this is the main idea. We can use a straight line, a tangent line, to approximate values on a curve as long as it's close. And the idea is that as we zoom in, any curve is going to look more and more straight. Okay, and therefore the better that tangent line approximation becomes, the closer we are to the point of tangency.